So continuing in our financial literacy portion of the course, let's learn effective rate of interest. Okay. What this is if you took what interest rate you were given and the number of compoundings and said, in order to end up with the same amount after 1 year of simple interest, what would the simple interest have been? It's just a convenient way of comparing, oh, this one person is offering 5% compounded every week. This other person is offering 5.5%, but only compounded every month. Which one is better? What you do is you convert them both to an effective rate of interest. What would the simple interest rate be over the span of a year? And then you can compare them more easily. So that's R sub E, your effective interest rate, given by these formulas here, if this is a compounding version or the continuous version. Okay. So here's an example. You want to invest. You're going to buy a certificate of deposit. You give the bank money. And instead of, nowadays checking accounts with the bank don't really pay you any interest. In fact, they usually charge you money for the pleasure of holding your money. But what you can do is you can purchase a CD. This basically says, at some minimum, usually 1,000, I think, for some quantity of money, you give them, and essentially you're not allowed to touch it for usually a year. In this example, it's a 5-year certificate of deposit. So you're guaranteeing the bank you are not going to take this money for 5 years. They will pay you interest, and what they end up doing is they take your money and they lend it to other businesses that they charge interest on, and then they use some of that interest to grow your certificate of deposit. This is how banks work. So you want to buy a 5-year deposit. You visit 3 banks. You get 2.17% monthly compounding, 2.18% quarterly compounding, or 2.16% daily compounding. There's no obvious one that's worse, okay? Basically, they follow this scale of a slightly lower rate at more frequent compounding. 2.18 is the highest rate, but only once a quarter. 2.17 would be every month, and 2.16 is lowest, but it's compounded every day. So which one's actually the best? So we're going to compute the effective rates of interest and see which one is highest. So for American Express, we just plug it into this formula. Their rate was 2.17%, and it was monthly, so that makes the number of compounding periods 12. We plug this into a calculator, and we get about 21.92%. Sorry, 2.192%. 21% would be ridiculous. The other bank, okay, it's a slightly higher rate, but a lower number of compounding periods. We compute it out, and we get, ooh, just a bit higher. That's nice. What about that bank that was offering daily compounding? Has a lower interest rate, and it's actually worse. It's the worst one of the 3. So the best deal is actually the quarter compounding at the highest rate. In this particular choice of rates and compounding periods, I'm not saying no matter what, go with the highest rate. You actually have to compare them. And in this example, the highest rate with the smallest number of compounding periods actually worked out. Okay, so that's who's giving you the best deal. So a similar notion is what's called present value. This is a sort of like saying, instead of taking my money and putting it in the bank today and asking what will it be worth in the future, this is saying I want to have a certain amount of money in the future. How much money do I need today in order to get there? So this is a financial planning asset. And it's not just like people saying, oh, I need to save $10,000 for such and such expense. How do I plan for that? It's actually used all the time in business applications as well, because what will happen will be like you have business A and business B, and business A pledges. They want to purchase something from business B, let's just say, but they don't have any money. What they do is they say, a year from now, I'll give you $1 million. But business B needs money now in order to like produce the items. Okay, it's going to take them time to produce the items, but they're not going to get paid until they finish. So what they can do is they can say, I am certain a year from now I'm going to have $1 million. So I'm going to go to a bank and say, look, I have this from them. They're pledging to give me $1 million a year from now. Since you're offering a certain interest rate on like business deposits, can you give me a loan based on the present value of the money? What that $1 million a year from now is worth today, give me that money so I can actually produce the items. Then I'll make them, I will sell them, I'll get that money and pay you back, and you'll have made your interest. Okay, so this has been up here for a while. Sorry, hopefully we've copied down this formula. It's really the exact same as the previous interest rate formulas, but the exponent has a minus sign. Because instead of time going from now into the future, it's going from a future value into the present. So time is sort of flowing backwards, so you put a minus sign on it. This is a handy trick in physics too. If you want time to flow backwards, just make it negative. Okay. So suppose you have a bond. It's what's called zero coupon, meaning it doesn't produce any interest, which for the purpose of this problem makes it simpler. You know 10 years from now it will be worth exactly $1,000. That's the offer. Okay, I'm pledging, hey, I've got this bond. 10 years from now, you can redeem it for $1,000. Suppose you want to compute the present value of that bond, how much you think it's worth today, assuming two different things, 7% compounded monthly, or 6% compounded continuously. One way to think of this is, if I have my money, I can purchase this bond, or I can invest it at 7% compounded monthly. If I invest at 7% compounded monthly, how much money would I need today to end up with $1,000 10 years from now? That's how much I think this bond is worth, because I have this 7% investment opportunity in front of me. So rather than buy the bond, I might just want to invest my money in this other thing, and I need to see which one's better. So what would be the equivalent amount of money today if I had 7% compounded monthly in order to end up with $1,000 to now? We just used the formula that was given on the previous page. So the present value is P, the future value is A, the rate is 0.07, the number of compounding periods is 12 because it was compounded monthly, and the number of years is 10. By the way, the way this formula works, remember, is that we had the previous formula A equals P 1 plus R over N to the NT, right? All you have to do is divide both sides by 1 plus R over N to the NT. And on the right-hand side, you just get P. And on the left, I just express this as having a negative exponent. So I get P is A times 1 plus R over N to the negative NT, rather than dividing by it to the NT power. It's the same formula as the other one. You're just switching whether you know the principal and want to find the future value, or in this version, do you know the future value and you want to find the principal. That's the only difference. Anyway, continuing on. Whoops. So we plug in the various values and compute $497.60. That's how much money today is worth $1,000 10 years from now, assuming 7% compounded monthly. So that's what I would be willing to pay for that bond. On the other hand, continuous compounding uses a slightly different formula, and we're using a different interest rate, 6% instead of 7%. There, I think that bond is worth $548.81. So for 6% compounded continuously, I would pay $548.81 for the bond. A similar problem, what interest rate compounded annually is needed to double an investment in 7 years? So in other words, I want what's called the doubling time to be 7 years. So what interest rate would be equivalent? Compounded every year, I want to double my money in 7 years. So if P were the principal, then the amount in the future would be 2 times P. So let A be 2 times P. I want once per year, so that's N equals 1. 7 years, that's T equals 7, and now the only unknown is R. So we take this formula, and we say, I want, sorry, this formula should have been A over here and P over there. I want A to be 2P. N is 1, so we can kind of ignore this, and we can ignore this N, and then T is 7. Well, now if I divide both sides by P, the P actually didn't matter. You can also think of this as whatever the principal is doesn't really matter. I just want to double it. So $1 could go to 2. So I could let this be 1, and I could just have let this be 2 to begin with. But now we can solve this the following way. This is okay, but it's a little weird. What I would actually do is I would now take the natural log of both sides. Then the power property brings down this 7. Then I would divide both sides by 7. I'm going to come over to the top of the left column here. So if I divide both sides by 7, on one hand I'll have a log of 1 plus R, and on the other side I'll have a natural log of 2 over 7. Now I'm trying to solve for R, remember. It's buried underneath this natural log, so I can exponentiate this. I can convert this into an exponential expression and say e to the natural log of 2 over 7 is 1 plus r, and now I can subtract 1. R is e to the natural log of 2 over 7 minus 1, which is exactly the same thing. Okay, e to the natural log of 2 over 7 is the same thing as 2 to the 1/7. Anyway, once you do that minus 1, you get about 10.4%. So if you want to double your money in 7 years, you need to get 10.4%, which is pretty aggressive. That's an awfully high payout. In other words, 7 years is an optimistic time frame to double your money. So suppose I can only make 6%, but it's compounded continuously. How long will it take to double money? And how long will it take to triple? So flip back, find those formulas, see which one of these is going to be useful. How long, in other words, what time is necessary to double in value? So P becomes 2P, so A is 2P. R is 6%, 0.06. T is the unknown, but I'm compounded continuously, so use that formula. And then all you have to do for part B is, instead of going from P principal to 2P, just go from P to 3P. Okay, so we're just going to use the continuous compounding interest formula, and again, the amount A will be twice the principal. So I just replace A with 2P, and I replace R with 0.06. The P's can be canceled off. Okay, when computing something like doubling time or tripling time, the actual principal amount will always cancel. Now take a log of both sides, divide by 0.06, and you get, it'll take you about 11.55 years. Definitely longer than the 7 years in the previous problem, but a bit more realistic. So it takes about 12 years, or 11.5, to double the investment. To triple the investment, very little changes. You just use A equals 3P instead of 2P. So it's really the same work, it's just you have a 3 over there instead of a 2, which means I have a log 3 instead of a log 2, and it works out to be about 18.3 years. So here's what we found. So for P, to become twice as much took about 12 years. So now, how long do I have to wait for it to become 3P? Now, the naive and incorrect approach is to say, I added P dollars, and it took 12 years. So since I want to add P dollars again, it takes another 12 years? No. Okay. Because I have more money to start with, it will take less time. We just determined that this length overall is about 18 years, which means this step right here only took 6. So while it took me 12 years to get P dollars, starting from P to go to 2P, it only takes me 6 more years to go from 2P to 3P. To go from 3 to 4 will take less time again. So it speeds up. Having more money makes you make more money. It's the way compound interest works. Okay, so that's the end of this section. This was all financial applications. We'll come back in the next section and we'll learn some scientific applications.